Hello dear viewers, welcome to our session of the day. Today's discussion is all about the polar form of complex numbers. Before we proceed, feel free to like, comment and share this video, and why not subscribe to the YouTube channel for more mathematical content. And also, if you want a one-on-one online tutorial session, you can email me at the address pjanko@mathtutorialchampion.co.za. Let's dive into our conversation of the day. This is an overview of what we are going to discuss all through. We are going to look at the polar coordinate system. We are going to look at some terminology associated with the polar form of a complex number, and we are going to end with an example on how to convert a complex number from rectangular form to polar form. Let's talk about the polar coordinate system. To introduce the polar coordinate system, let's consider this argon diagram. On this argon diagram, we have chosen an arbitrary complex number z equals to x plus iy. Here is a complex number. How do we represent it on the argon diagram? We move on the real part to locate x, and we look for the corresponding y coordinate, which is y here. After that, we draw an arrow from the origin to the point, and we represent arrow to be the length of that arrow, and theta to be the angle between the real part and the complex number, and that angle is represented by theta. From our knowledge of trigonometry, I hope you still remember the basics of our trigonometry rules. Saying this is a right angle triangle, we can apply what we usually call the SOHCAHTOA rule. Therefore, we know that the cosine of our angle theta is given by the adjacent over the hypotenuse. The adjacent is indeed the length x, the hypotenuse is the length r. Therefore, x can be written as cos theta. Don't forget that x is indeed the real part of our complex number. So we can replace the real part of our complex number x by the value r times cos theta. Still, from our knowledge of trigonometry, we know that sine of theta is equals to opposite over hypotenuse. What is our opposite here? The value of our opposite here is y divided by hypotenuse, which is r. Therefore, y can be written as r times sine theta. So we can have x, which is alternatively written as r times cos theta, and we have y, which can be written as r sine theta. Remember that our complex number z is given by x plus I times y. If we replace our x by the value from trigonometry rules and y by the value from trigonometry rules, we are going to obtain z equals to r times cos theta plus I times r sine theta. If we factorize r, we are going to have z equals to r times cos theta plus I sine theta. This is what we call the polar form of a complex number z. Based on that, let's look at a few terms associated with the polar form of a complex number. The first term we would like to explain here is what we call the modulus or the magnitude of the complex number z. The magnitude of the complex number z is that value r given by the formula the square root of x squared plus y squared. So this is the formula used to obtain the modulus or the magnitude of the complex number. And theta is called what we call the argument of z, and denoted by argz. And still, how do we obtain theta? We obtain theta by looking for the arctan of y divided by x. That is how we obtain the argument of the complex number. Take note that we cannot talk about argument without talking about the principal value argz, which is that principal value used to represent the complex number in polar form. So take note that the principal value z lies in the interval minus pi pi. So we always make sure that the principal value lies in the interval minus pi. So alternatively, if our value theta does not lie in this interval, it is left for us to remember that we can use the formula arc z is equals to the principal value arc z plus or minus 2n pi. This implies that from this equation, we can obtain the alternative equation arc z to be equals to the argument z plus and minus 2n pi. This formula is very important when we want to represent a complex number in the polar form. Take into consideration the value theta that will be used to represent the complex number in polar form should lie in this interval. The principal value here should always lie in the interval minus pi. You will see why this equation is important in the upcoming examples. For the meantime, let's look at how we can convert a complex number which lies in the first quadrant to polar form. So remember, when you're given a complex number and asked to convert, always check in which quadrant does this complex number lie. So we can see that here 1 is positive, so we can locate our 1 here. And the value of the imaginary part here is 1 here, so we can locate 1 here. So we have our complex number. Now we draw the arrow from the origin to that point. Remember that this is the imaginary, the real part, the real part of our complex number. And this is the imaginary part. So this implies the complex number lies in the first quadrant. So for all complex numbers in the first quadrant, the reference angle is indeed the same. Let's represent the reference angle by alpha, is the same as that argument, or is the same as the argument which is the same as the principal argument. Okay, and remember this is represented by arctan of y over x. And what is our y over x here? Is indeed arctan of 1 divided by 1, because in this case x is 1 and y is 1, so we're going to have arctan of 1, and the answer here is pi over 4. We can see that pi over 4 lies in the interval minus pi. So this represents the principal value we are going to use in the representation of our complex number in polar form. Now let's look for the modulus. Remember the formula used for the modulus is given by x squared plus y squared. So the square root of x squared plus y squared. So we are going to have the square root of 1 squared plus 1 squared. And the answer is the square root of 2. Therefore, z is indeed our square root of 2 times cosine of pi over 4 plus I sine pi over 4. And that is it. As simple as that. So for complex number in the first quadrant, is straightforward, no complications. This leads us to the end of our video. What did we look at through this conversation? We've discussed the polar coordinate system, how to represent a complex number in a polar form for arbitrary complex number z equals to x times iy. We've looked at a few terminologies like the magnitude or the modulus, like the argument of the complex number, and we've also discussed the formulas used to find these various terms. We've equally observed how to convert a complex number from rectangular form to polar form, and precisely we choose the example whereby our complex number lies on the first quadrant. So watch out for the upcoming videos. We are going to look at more examples for complex number which lies on the second, third, and fourth quadrant. Once more, thank you for following up to the end. Feel free to like, share, comment this video if this was very interesting, and also feel free to subscribe to this YouTube channel. Thank you once more. See you in the next video.